Welcome back to Engineering Acoustics. Hi, this is Professor Ryan Harne. In this video, we'll gain new insight into how pairs of acoustic sources radiate waves into the far field.
So let's get started. We've just learned that when the source size is small with respect to the wavelength, our basic monopole acoustic source is called a point source. And the acoustic pressure distribution from that point source is shown as we see here on the right. Now we have a complex amplitude divided by R with an e to the j omega t minus kr. In fact, this is the same as what we found originally for spherical waves, in general for spherical waves. So our original assumption regarding the complex exponential form of acoustic pressure for spherical waves was in fact correct, because it agrees with what we found for the point source. But what if the situation became much more complex than a single spherical wave source? What if we have two? This is the first step from going from a single source to multiple sources where sound all converges to a common field point. So we can ask the question, what is the total acoustic field? Because we've modeled our acoustic sources according to an assumption of linearity, we can easily superpose the acoustic pressure contributions from multiple sources. So let's consider that the first source, P1, that has distance R1 to the source, has complex amplitude, complex A sub 1, divided by R1, and then has a complex exponential e to the j of omega 1 t minus k1 r1. We use both omega 1 and k1 because they may, for instance, have distinct frequencies and wave numbers compared to the source 2. So point 2 has acoustic pressure contribution P sub 2. It's equal to the amplitude complex A sub 2 divided by R2, and then the complex exponential e to the j omega 2 t minus k2 r2. So in general, due to this superposition we could take advantage of, P as a function of RT at the field point requires us to identify some origin. So let's use X and Y as our coordinate system, and the R travels from the origin to that field point. The acoustic pressure there is then P1, which is its function of R1 and T, plus P2, which is a function of its R2 and T. We need to simplify this expression in order to compute further. So for incoherent sources, when the frequencies omega 1 and omega 2 are different, omega 1 is not equal to omega 2, we have to take an RMS sum. In other words, the P RMS is equal to the root of P RMS 1 squared plus P RMS 2 squared. This is the more general case when the sound sources are either broadband or simply have different frequencies. But what if they do have the same frequency? In the case when omega 1 is equal to omega 2, which we'll just call omega, so likewise k1 is equal to k2, which we'll just call k, we need to simplify our expression. So the acoustic pressure then can become P as a function of R and T is equal to complex A1 divided by R1 multiplied by e to the j omega t And using the multiplication law for exponentials, we also have this multiplied with e to the minus j k r1. And to this we add the contribution from source 2, complex amplitude A2 divided by R2, and then e to the j omega t multiplied by e to the minus j k r2. Summing this up, we have that the total acoustic pressure, P as a function of R and T, is equal to a bracketed term and a common e to the j omega t outside of that. The bracketed terms contribute the amplitude differences and the phase differences for these coherent sources. The amplitude differences would be complex A1 divided by R1 for the first source, and the second source, complex amplitude A2 divided by R2. The phase contributions for the first source would be e to the minus j k r1, and the phase contributions for the second source would be e to the minus j k r2. It's important to recognize, just as before, only the real part of this total acoustic pressure is physical. It's measurable. And what we see is that this product Kr is going to play a large role to determine the total acoustic pressure, since it plays the role of phase. And we intuitively know that waves with out of phase contributions can cancel when they are coherent. So how does this in general turn out? Well, we can't simplify the situation for all cases, but we can simplify the math when the sources are far away from the field point. So if this is the case, we've drawn the scenario here. We have a source gap D, where the sources are D divided by 2 away from their respective origins on the x-axis. And the field point at location R and theta is very far away from the origin where these point sources are nearly placed. So let's consider this case. We've got y and x, and we're going to consider our point sources 1 and 2 are very, very far away from the field point. We have our R and theta. Now in this case, when the field point is very far away, the individual R1s and R2s are effectively parallel with R. So by considering the geometry involved, we know that this distance that is being sketched here is a distance d on 2 sine theta. That's also the same distance for this distance between point source 2 and the radial location for the origin. So what we can do is say that when R divided by D is much greater than 1, we can approximate the R1 and R2 that are the individual radial distances from the point sources to the field point. In other words, R1 is approximately equal to R minus D divided by 2 sine theta. And R2 is approximately equal to R plus this D on 2 sine theta. This allows us to simplify our total acoustic pressure relation. This is called the geometric far field, when we know that the field point location R is much further away than a dimension D, which is sometimes called a characteristic dimension, the largest dimension of the acoustic source overall. When R divided by D is much greater than 1, we call this the geometric far field. What we can do is simplify our acoustic pressure by substituting in our approximations for R1 and R2. Now, in the denominators, these corrections, minus d on 2 sine theta and plus d on 2 sine theta, we need to recognize that we've already written that r divided by d is much greater than 1. So that means that r is much greater than either plus or minus d on 2 sine theta. So in other words, these corrections in the denominators are effectively 0, and we can get rid of them. On the other hand, in the complex exponentials, we cannot get rid of these. The reason is because this complex exponential represents a sinusoid, and the argument of a sinusoid repeats the function's result every 2 pi. So these are important phase contributions. So our simplification of the acoustic pressure, P as a function of R and T, is equal to amplitude A divided by R, where we've taken our complex amplitude A1 and said it's going to be equal to our complex amplitude A2, and it's just going to be a purely real amplitude A. We can bring this component out, A divided by R, e to the j omega t minus kr, and then it's multiplied by a bracketed term that includes only the phase contributions, e to the minus j k divided by d on 2 times sine theta plus e to the positive j kd on 2 multiplied by sine theta. This can be further simplified into an equation that reads a on r e to the j omega t minus kr multiplied by what's now simplified in the bracketed term as 2 cosine phi. We use Euler's identity to determine this final component at the right here. And what we write for simplification is this capital phi is equal to kd on 2 sine theta. As a result, we found that the far field acoustic pressure for the point source pair is given by a radial dependence 2 times A on R, the complex exponential that shows the time variation e to the j omega t minus kr, and finally a trigonometric part cosine of phi. When we take the magnitude of this result, we find that the far field acoustic pressure amplitude magnitude of our pressure P is equal to a component 2 times A on R multiplied by the magnitude of cosine of KD on 2 sine theta. We can decouple this acoustic pressure amplitude into 2 important parts. We have the far field axial pressure amplitude, which is the first part, showing the radial dependence in the variable r. This is written as capital P sub ax, which is a function only of r. The second component in the modulus with the trigonometric functions is called the beam pattern. This demonstrates the angular dependence of the sound field, and this is given as a capital H as a function of theta, so that our complex acoustic pressure amplitude P is equal to, in general, P sub ax as a function only of r, and the beam pattern, capital H, only as a function of theta. We can learn a lot by studying these components, because this result is in general correct. Let's specifically study the beam pattern, since we're already familiar with the 1 on r dependence of acoustic pressure amplitude. The beam pattern that we've computed is the modulus of cosine, that's a function of kd on 2 times sine theta. Let's plot this out for several combinations of the product kd, recognizing that kd is equal to 2 pi d on lambda. we would get this result, for instance, if we coded this up in MATLAB. For KD is small and less than 1, this means that the wavelength is large compared to the characteristic dimension D. And we see that the beam pattern is flat in the blue curve. As KD increases and the characteristic dimension is gradually larger than the size of the wavelength, for instance in the case of KD is 2, we find that there is a reduction of the beam pattern in value as the elevation angle in degrees increases. The beam pattern here is shown in dB, so this would be beam pattern dB is equal to 10 log 10 of h. Now going to a case when KD is 4 and the characteristic dimension is notably larger than the wavelength, what we find are these nulls, these low values of the beam pattern. Admittedly, this presentation of the plot is a little bit arbitrary and complex to understand. More often the beam pattern is plotted in a polar sense. What this means is that we can envision our sources as being positioned somewhere close to this origin. The code used to generate this plot is shown at the bottom left. And the way that this plot is interpreted, we look at the angular dependence of theta as it moves along a constant radius. And this is in the geometric far field. What this means is that for KD is equal to 1/4 or 0.25, there is no change in the beam pattern. So this is a long wavelength case compared to the characteristic dimension. And in this case, all of the sound is uniformly radiated in all directions angularly. But when the frequency goes up and the KD goes up, this means that at the extremities, when the angle is close to 90 degrees, we have slightly less sound radiated to those locations than we have when theta is equal to 0. And finally, in the case when KD is equal to 4, we have a null. Sometimes called a node. And this is where there's cancellation due to interference. Sound is, in the nominal case, not radiated at all at that angular location. So if we were to take a rope and begin at the location where theta is d, and someone tied this rope near this origin, and we gradually walked in increasing theta, as we get to a location around 50 degrees in elevation angle, we would hear nothing, given this wavelength and frequency. There are things that are important to note here, is that for this point source pair, this location, theta is equal to 0, it's called broadside. For this point source pair, broadside will always be a maxima, whether global or local, for the acoustic pressure distribution in the beam pattern. This is the location of the major lobe. What major lobe indicates is the angular region where the acoustic pressure is greatest. These two features over here that are being sketched, which are adjacent to the major lobe, these are called side lobes. They are in similar character as the major lobe because they are also sources of constructive interference, but they're lesser in magnitude of the beam pattern, and as a result, they're not as significant to radiate sound. For this point source pair combination, sound is uniformly greatest in delivery to broadside.
Hey everyone, we're going to test out constructive and destructive interference. So let me show you what we've set up.
Here we have a pair of speakers, an amplifier, and a function generator driven by an amp. The speakers are approximately 24 inches apart from center to center, and if we use MATLAB to approximate the beam pattern for this configuration, plugging in our numbers of frequency, we'll drive this at 500 Hertz. They're spaced apart by about 24 inches, which is around 58 centimeters, and the remainder of the code is shown. If we run this code, we see a beam pattern that looks like this. So at approximately 30-35 degrees off from broadside, we should hear a null, or instead we should not hear a null. So let's try it out. So we have the speakers playing at 500 Hertz. Let's walk at a constant radius around this pair of sources to see the beam pattern ourselves. We have a rope to keep us a constant distance from our speaker pair. Here we go. We are at broadside. Let's walk towards the first node by keeping this constant radial distance. Here we are at the first node, the first knell. Let's go back to broadside to hear how that compares. And back to the node again. Where does this term come from? Broadside is the term that means the direction of sound radiation perpendicular to the line between sources. The term has a unique history. It in fact comes from maritime adventures, whether in more recent times with large turret guns, or back in the era of ships and cannons. When a ship would turn, pointing all of its guns perpendicular to the axis of the ship, this term was referred to as broadside. All guns were brought broadside and fired at once. This is, of course, the most harrowing and dangerous way to face a ship, whether in ancient times or modern times. But the word continues to be used to date in acoustics to refer to the sound radiation when all of the sound sources converge their acoustic pressure distributions to the field point. So let's summarize what we've learned. We've learned that the overall sound delivered by a pair of point sources is simply the superposition. And the superposition of the acoustic pressures when the sources are incoherent is as easy as taking an RMS sum. But when the sources are coherent, we need to take into account phase. And in the far field, specifically the geometric far field, we identify that there is a far field axial pressure amplitude and a beam pattern. The beam pattern is important because it identifies angular regions where we might have lobes or nodes where sound is more highly or less so concentrated. That's it for this video. In the next video, we'll more closely examine these interference patterns for pairs of acoustic sources.